So here I'm just writing the statement of Prohor's theorem, which I started to prove last class. And well, there's so much notation definitions involved in these things. But it's good to remember some of it, at least. Well, you have your complete separable metric space. You have the space of probability measures over that metric space with the Borel sigma field. And then you have a subset here, non-empty. And the theorem says that S is relatively compact. Meaning that every sequence of measures in here has a convergent subsequence, in the sense of weak convergence. If and only if S is tight, meaning that for all epsilon there exists a compact subset of X, such that for all P and S, P of K epsilon is greater than 1 minus X. So this is the theorem, and we have already discussed one special case of it, which is a case when X itself is compact. Okay. So I want to remind you of what of how this proof goes. And right, so basically, let's talk about the compact case first. First thing is that maybe I should say something on the effect. Okay, so we have the space of continuous functions, right? So usually when we talk about weak convergence, we talk about the convergence of integrals of bounded continuous functions. All continuous functions here are bounded. And we have this space of continuous linear functionals. So I'm going to maybe give a little bit more detail. Last time. And actually I want to consider a subspace here. So a linear functional is just, well, a linear mapping from C, XR to R. And it's continuous, well, if it's a continuous function. And I want to consider with the linear functions that are positive, right? That is, they map positive functions to positive numbers, right? So when I say for all f, of course for all f in this space, right? And basically the proof of Prohor's theorem is that there's a first step that any subset S of the space, okay, let me say S, which is bounded, and boundedness really means, that in this case, because the linear functions are positive, means that sup for L belonging to S of L of 1 is finite. Is, well, any such subset is relatively compact. This is what I said was a consequence of Banach-Waloglu theorem and the fact that the weak topology here is metrizable. But the weak star topology, so relatively compact for the weak star topology. And let me say what this means. So it means that for all sequences contained in S, you can find a subsequence and another linear functional such that for all f in C, L and K of F converges to L of F. Right, so weak star convergence means that a sequence of linear functions converges to L in this weak star sense if this sequence applied to a fixed function converges to L applied to that fixed function for all F, for all functions. And the second part of the proof is just to say that this space here, this space of dual, this dual space when you restrict to positive linear functions is in one-on-one correspondence with finite measures over x dx. So this is the Ries-Markov-Kakutani or Ries-Kakutani-Markov theorem. It says that if you have a positive linear functional, you have a corresponding positive measure, okay? And vice versa. And so this statement here, you can think that it's a statement about measures, right? So this is saying you take a sequence of measures, and well, you take a subset of the space of measures, where this measure, the whole space, is bounded. Then for any sequence of measures in that set, you can find a convergent subsequence. So this is more or less what we want here, except that you have to check that when you take linear functionals corresponding to probability measures, the thing that you converge to is also a probability measure. But that's sort of trivial because you just look at what the functionals do to the function that's constant equal to 1, and you have to be convergent, so that's essentially done. So now we're going to discuss the general case, right? And we're going to see that this, one of the reasons why I'm repeating this proof is that the general case is going to follow from this somehow. Right, so let's see what we have here, right? And so I'm going to prove first the this direction, that tightness implies relatively compact, no, sorry, I'm going to prove the other direction first, which is the easy one. And essentially, this easy direction is just a matter of combining things we know. Okay, so. Right, so we want to say that if S is relatively compact, then S is tight. And what I'm going to do is I'm going to, okay, I'm going to do it by counterpositive, the counterpositive statement. Let's say that assume, okay, so this reaction, assume S is not tight. There exists an epsilon such that for all compact subsets of X, there exists a P in S with P of K less than 1 minus epsilon. Right? And okay. So let's see what's out of this. Just an epsilon for OK. So, well, let me call this PK measure. Right? So for any measure here, I have PK of K less than 1 minus epsilon. Right. Yeah. Now let's so actually what I want to consider is for each K compact, I want to consider let S of K correspond to the set of all P in S such that P of K is less than 1 minus epsilon. And right. So assume that S of K is infinite. Okay, so let's see. Right, so we know, and I'm forgetting so much. Right, okay, let's see. Assume that S of K is finite for some K. Right? I claim that. Okay, I should have said here that assume to get a contradiction. That S is not that, but is relatively compact. Okay, so this is important. So I claim that assuming that one of these sets is finite, that this leads to a contradiction. And how does it lead to a contradiction? Well, so I mean that this, so that this thing here leads to contradiction, so let me be clear. And the reason for that is the following. So we know, okay, so let S of K consist of a certain number of probability measures, which we're assuming to be finite, right? So for each I, we have that Qi of Ki is greater than or equal to 1 minus epsilon for some Ki, right? So we know that a set consisting of a single measure is tight, right? So we can always find a compact set like this. And because the union of finitely many compact sets is also compact, we deduce that Qi of K1 up to AK union this K here is greater than 1 minus epsilon for all I. And also P of this union is greater than P of K, which is greater than or equal to 1 minus epsilon for all P that do not belong to SK. Right? So I'm just saying, okay, so if this set here is finite, then there's a contradiction because, well, I can remember that I assume this thing here, that there exists an epsilon such that for any compact set, you have this. Right? So I'm saying that you shouldn't be able to find a compact set such that for all measures in S, you have this condition. Right? So then the point is that this is compact. But here I've done just that. I'll find a compact set that's good for these measures, but I also found a compact set which is good for all the other measures, because K was already good for the other measures, right? So, okay. So, A is true. That is for all K, S of K is infinite. Right? Okay. But, right, so let's see. So we also have that if K prime is contained in K, that Sk prime is contained in S of K. No, sorry, it's the other way. Right? So just saying, okay, so what's Sk prime? It's a set of measures that put mass less than 1 minus epsilon over K prime. So if P of K prime is less than 1 minus epsilon, certainly P of K is also less than 1 minus epsilon. Right? Okay. Right, so now let's do the proof. So, oh no! Okay, so I did something slightly inconvenient here, which I need to remedy here, because I should have had less than or equal here, and then everything sort of changes. So because I have to do this, and then I do this, and I do this, and I do this. Okay, now it's fine. And there's another one. Yeah, no, okay, that's fine. Okay, because I'm gonna do something else here, which is just to say I'm gonna take the closure of these sets. And yeah, but I forgot. Well, there's a bunch of things I should have done before that I haven't done. Well, okay. Let me say what I want to do now. Okay, so it's so yeah. So yeah, the things that I didn't define. I should have defined the topology before. Otherwise, I'm in deep trouble. What do I do now? Because so what I want to argue, I mean, if when I want to argue, okay, you have this, and you have this, and you have this. I want to argue that these sets here, well, okay, so we're assuming that S is relatively compact, right? So if you have a sequence of points in S, it converges to it has a convergent subsequence. So what I'd like to say is that the closure of S is compact, and that this closure is also compact. But that's not really the way to do it unless you define the topology. And I forgot to do that. Because then we have okay, so I'm just going to do this. I'm just going to go back. And I'm going to, right, so I want to do a proof that's more topological, the way, let's see. No, but for that I need so many more things. Right, so let me just say, okay, if you believe this thing here, that these sets are compact, and they have this sort of order by inclusion, right? You can find then basically, if you take a, what is it called? No, okay, unless I define the topology, and for that I need to do Stone-Weierstrass. I need to do all sorts of other things that I haven't done yet. Yeah, because I mean, what I want to use is something that says that if you have a connection of compact sets and they have the finite intersection property, then they have non-empty intersection. But that's, unless I define the topology first, that's not going to be very clear. So let me see, what can I do here? So I can say I have the S relatively compact, so this is epsilon, blah, blah, blah. Right. No, yeah, but yeah, that's. That's not going to be very good. Okay, so here's what I'm going to do. So I'm gonna just go back and do everything from scratch. So just from this point. I'm sorry about this. Okay. Right, so what I'm going to do is that I'm going to start with the other direction, the hard direction. And then from that proof, what I want to do is going to become clear is essentially that, okay, so, yeah, that's essentially that if you want to have a convergence sequence, well, let me state what I have here. And then I think that everything will become clear. So for each k, right, so now I'm proving that if you have a tight family, every sequence has a convergent subsequence. So let me take a sequence in S. So for each j and n, let k sub j be a compact subset of X with Pn of kj greater than 1 minus 2 to minus j. Well, you put your favorite sequence that goes to 0 here for all n. Yeah. And, right. So, and actually, I mean, we can assume without loss that K1 is contained in K2, which is contained in K3, all the way, right? Because instead of putting Kj here, you can put K1, union K2 up to Kj, and it still satisfies this property. Right, so I can assume that it's a nested increasing sequence of compact sets. Okay. So now, from A and B for the compact Ks, okay, for each Jn, I have a measure which is Pjn of a set A, which I define to be equal to Pn of A union K, J. Right? So each Pjn is a measure over x dx, which is supported on Kj, right? And well, I'm gonna do a slight abuse here. Just gonna say, well, if you pretend these measures are actually measures on the compact set Kj, then we know that we have relatively compactness over this compact set. So by the compact case, and that's really not a grave matter. Know that and I'm going to put it like this, that for all subsequences of these measures, you can find a subsequence such that Pj and Kl converges weakly. Well, okay, such that for all f such, okay, I should say such that for all continuous functions over continuous bounded functions over x, right, I have that Pj and Kl of f indicator 1kj converges to some measure Pj f1kj. Right? So here I'm saying, well, if you take a continuous bounded function over the whole of x and you're restricted, right? So this is really a restriction here. If you're restricted, now this is a continuous function over the compact set kj. And because I know that the set of measures with bounded mass over a compact set is relatively compact, right? So it's always, I mean, that I have this compactness property, rather, that allows me to deduce this. Okay, again, what am I saying here? This is a sequence of finite measures of mass less than 1, right? Because the way I define things. So given a sequence of finite measures of mass less than 1, I come to this theorem and I look not at x itself, but at kj. So I have a sequence of measures over this set kj, which is compact, right? With induced topology, induced sigma field, and everything. So given such a sequence, I can find a convergence subsequence of measures, right? These are not necessarily probability measures. Well, all I know is that Pj of Kj is less than or equal to 1. Right? So in general, it's going to be less than 1. Well, what I do know is that if I take a continuous function over the whole set x and I restrict it to Kj, I have a continuous function over the compact set Kj. And therefore, just by reconvergence, the integrals must converge. Right? Okay. Now, I want to say something which is, I'm going to say it and then try to explain it by the diagonal trick. We can extract the subsequence. I'm just going to say what this is, such that for all j and for all f in the continuous functions from x to r, that I have that Pj of n sub k of s restricted to kj converges to Pj of f 1 kj. And let's say what I mean by diagonal trick. I mean, this is related to things you've probably seen at some point in your lives, which is you have a bunch of sequences and you want to extract the convergence subsequence for all of them. Right? So how does that work? Well, it works like this. So you have P1, P2, P3, P4, P5, right? So this is the whole sequence. So now, first of all, I want P1 the sequence of P1s to converge, sorry, this is 1, 3, this is 1, 5. So what I mean by this drawing here is that I can always find I have a sequence of measures up there, and now I can, this sequence here, if I look at the measures restricted to the compact set K1, I know it has a convergent subsequence. So I can find a subset of the indices such that this converges. And now I can find, within the subsequence, I can find a subsequence that where, say, the two measures converge. It's something like this. Right? So I can find another subset of indices such that converges. So in general, what I'm going to do is I take n0 equal to n, and I take ni to be a subset of ni minus 1, such that nj, such that pj n for n restricted to nj is convergent in the sense of is weakly convergent. Where right? And then and then what you do is right, so this we can always do, right? Because okay, that's because we know we can always find convergent subsequences from subsequences of subsequences. And now if you want to do the diagonal trick, well, diagonal trick simply consists of saying that nk, well, okay, you define n0 however you want, say equal to 1, and nk to be the minimum, say, of n sub k minus the elements you have defined so far. And if you do this, you obtain a subsequence. Well, it's not contained in nj for all j, but it's essentially contained in nj for all j. So except for a finite number of terms, you have that it's contained in n sub j for all j, and therefore you have this convergence for all j. Right. So this is what the diagonal trick consists of. Okay. So now we have this thing here. We have this convergence. So what else do we have? So in some sense, well, these measures here, so the intuition now is that there exists a measure P such that for all j, P of A intersection Kj is equal to Pj to this limit that we define. Okay. So this thing we're defining here is right, so I remember I defined a measure for each compact set. So a sequence of measures for each compact set. Now for each compact set, I obtain a limiting measure. Right? But I don't want to obtain a measure for each compact set. I want to obtain a measure for the whole space. And the intuition is that this measure of the whole space is such that when you restrict it to each compact set, you get the measure corresponding to that compact set. So how are we going to define this? So an important point is just from the way the measures are defined, you have that Pn j of A is less than Pn j plus 1 of A for all j in n and for all A in the Borel sigma field. Right? So you have this increasing structure. And from this, you define, well, how do you obtain the pj's without the n, right? These are limits of these measures, right? When n goes to infinity along a subsequence. Therefore, you have that pj of A is less than or equal to pj plus 1 of A for all A and for all j. Right? So the way I'm going to define p, and it's not obvious that it gives you a measure, though we had an exercise last class, it's just, well, we define p of A as the limit in J of P sub J of A. And it's clear that this limit exists, and it's because it's an increasing sequence of arrows, right? Okay, so what about this? So we need to check that it's indeed a probability measure. Well, okay, so there are a few things that we need to check, right? So one of them is that 0 is less than PA is less than P of x, which is 1. Okay, that, well, okay, is the measure of the empty set 0? I should start with this. Okay, why is P of 0 equal to 0? Well, Pnj of, P of the empty set equal to 0. So Pnj of the empty set is always 0, right? So this limit exists and is equal to 0 for all j, and therefore you have this limit. So let me observe, before I notice that the whole space has measure 1, let me observe that for all j, P of kj is greater than 1 minus 1 to the j. Right? Why is that? Well, if you look, what is Pn of j of kj? Well, this is just Pn of kj, which is greater than 1 minus 1 to the j. Right? So the way to define this measure is by taking intersection with kj. So we get kj itself. So now if you have a larger value, a j prime that's, say, j plus 1, I'm going to say here. Or j plus L, whatever. Just from this monotonicity property, we know that it's even larger, right? So when we take limits, we see that Pj plus L is always larger than 1 minus 2 to the minus j. And therefore, we have that when you take the limit in this index up here, you get this problem. Right? And for the same reason, we have that P of A minus Pj of A is always less than or equal to 2 to the minus j. And this is going to be really important. Let's see why that is, right? So it's why is this true? Well, okay. Right, so this is equivalent to saying that for all L, P, J plus L of A minus Pj of A is less than or equal to 2 to the minus j, right? Because the limit of this when L goes to infinity is P of A. Now, if you look, right, these things are limits of Pn of whatever, right? What is this? So this is the measure of A intersection Kj. This is the measure of A intersection Kj plus L, right, under the measure Pn, right? So Pn of A intersection Kj plus L is exactly this thing here. Pn of A intersection Kj is exactly Pnj of A. So now now you have Pn of the set minus Pn of this other set. And this difference here is less than Pn of everything minus Kl. Kj, sorry. Right? So we have and this is, well, by the choice of Kj, this is less than 2 to the minus j. So we can say that the convergence of Pj to P is uniform. Okay. Right. So now there are more things we need to do. So, and I mean, in particular, we see from this that okay, there's 4 here. What's Px? Well, this is the limit of Pj of x, and this is the limit in J of the limit of a certain subsequence of Pj and sub k of x. This is just a definition, right? We found the convergence subsequence. And this thing here, this is just P and K of Kj, right? Again, by the definition. So this is larger than 1 minus 2 to the minus j. Right, so when you take the limit in j, you see that this is 1. So there's a... Oh. Right, so the only thing missing, and that's sort of the complicated thing, is to prove countable additivity of this measure. But that's really not hard. So now we notice that we remember that for, right? So each Pj is a measure, right? So it's not necessarily a probability measure. It might have less than 1, but each Pj is a measure, countably additive measure. So we're going to use that, right? So now, okay, 5. Take A1, A2. Belonging to the Borel sigma field, all disjoint. So we know that for all j, Pj of the union is equal to the sum. Now what happens when j goes to infinity? Well, this thing here goes to P of the union by definition, right? So this is the exercise that I assigned last class. If you have a sequence of measures that converges increasingly, right? So like these measures do, that you have, what is it called? That you have, that the limit is also a measure. So now I want to say that the sum of the limit of the sum is the sum of the limits, right? But the limits are increasing. So one way to prove it is just monotone convergence, right? So you have an integral of the counting measure of the natural numbers. But there are easier ways as well. Right? So you can just say, well, this is bounded by the sum of PAIs, and you can bound from below just by being clever. So you have in the end that this thing goes. So, okay, so sorry, without using monotone convergence, let's just say, well, you certainly have this inequality for all j. And on the other hand, if you truncate the sum for a fixed j, if you take the sum up to n, you get that this is less than this. Now when you take the limits on both sides, and you get the sum up to n is less than the probability of the union, and then you can increase n, and you get this is a lower bound as well. Right? But in any case, so this is good. Right, so we have a bunch of things. So what do we know? We have constructed a measure with the idea that it should satisfy this property here. Right? which is actually, I mean, now that we've shown that it's a measure, it's not hard to show this. Well, actually, we could have shown this from the beginning. But, well, we need to define P first, right? But it's just that if you take a set of this form, then it's very easy to see that Pj of A intersection Kj is equal to Pj plus 1, and you can check this. Okay? Right, so actually it follows from this thing here. So now, the last point is that we need to show that the sequence that we constructed, the subsequence, converges to P weakly. Okay? So we need to show that for all bounded continuous functions, and let's say that f takes values between 0 and 1, because that's without loss of generality. I mean, f is bounded and continuous, right? So we can look at positive and negative parts separately. We can rescale so that the maximum of f is 1. Now we're going to, okay, so we need to show this. And how do we do that? Okay, so we know that Pnkj of f, indicator 1k, j, converges to Pj of f1 of kj. Right, so that's the thing that we know. We know that we have weak limits over the compact sets. Right, so this we know and we know use it. There's something else that we know, which is this thing here, which we're going to use right now. Right? And right, so how do we okay, so I'm just going to notice a few things, okay? Okay, we have this convergence, and I want to compute the difference between these two integrals here. Right? And I claim this difference is small when j is large. Okay, this we know for all j. This is important. Why is this so? Right? So what is this measure here? Okay, so let me remember that we have this formula for the integral. Right? So we have the integral. F takes values between 0 and 1. So this is P and K of the set where f is larger than t, dt. This one I can write as the integral from 0 to 1 as P and K of the set where f is larger than t, intersection kj. Because this is exactly how you define this measure, right? You take the measure of a set, it's the measure of that set intersected with kj. So now I'm taking f restricted to kj. Sorry, this shouldn't be a 1, should be a restriction. So this is exactly what you get, right? So there are two things you can see about this expression. One is that it's bounded below by 0, because this integrand is always less than or equal to this. And it's bounded from above by the difference between these two measures, which is, well, okay, for each t, this difference is bounded by P and K of kj. Complement, sorry. And of course, this interval here is contained in 0 to the minus j, because we chose the compact sets that the complements always have measured to the minus j, right? So these things, if I take j large enough, this difference is less than epsilon. So now for pf minus pj of f restricted to kj, I have something similar. I have an integral from 0 to 1 of pf greater than t minus p, okay, it's less explicit, but let me put it like this. T, t. And now we can use that part 3 that I looked, right? Because this is less than 2 to the minus j. Well, this is certainly less than this, so this also belongs to 0 and 2 to the minus j. So now the argument's a pretty standard double limiting argument, right? So this limit is equal to this for all j. And the difference between this and this is arbitrarily small. Right, so if you want that this, okay, maybe we should write this just to make sure that everybody understands. And this is, okay, so what's the value of p and k of f minus p of f? Well, this is less than the limit in k, lim sup in k. This is less than lim sup in k of p and k of f minus p and kj of f minus pj of f, well, restricted to kj, f restricted to kj, plus 2, 1 minus j, which just comes from where I replace this guy by this guy. I pay the price of 2 to the minus j. And replace this guy by this guy. I pay the price of 2 to the minus j, so I pay that price twice. This limit, so this is less than 2 to the minus 1 minus j in the limit because this limit is 0. We know that it's 0. So what we show is that the lim sup is less than 2 to the 1 minus j for all j. And therefore it's 0. Okay, so the idea again is that somehow because we know that we have a sequence of compact sets that essentially exhausts the measure, right? So in the limit, those compact sets contain the whole measure Pn for all n. So because of that, we can use the compactness for the compact case to prove the theorem in this general setting. That's the idea. So, wow, there's some. Let me emphasize again that. You know, the theorem, the main theorem that we used to prove this in the compact case was this Ries-Kakotanyi-Markov theorem that says that every positive linear functional is represented by a measure. And this theorem is in general not true for Polish spaces, so you need to use some sort of trick. Okay, but let me argue that there are some parts of this proof that still work, okay? And even if you don't, okay, that even in kind of what I want to do now is I want to go back to that part of the proof that I didn't do because I hadn't introduced the topology on the space of measures, but and try to show you a way around this. So, right. So what's the main thing, right? So we define Pnj of A to be equal to PA intersection KJ. Sorry, to PN KJ. So then this is a definition, right? So we showed that there exists a sequence n sub k such that Pn KJ converges weakly to some Pj for all k, for all j. Right, so this diagonal trick, we've managed to prove that this converges weakly for all j simultaneously. Right? And converges weakly in the sense that the integrals of continuous functions converge. Let me put it this way. Right? And then we defined 2p to be the we argued that Pj converges from below to a measure P. Right, in this sense that Pj of A converges from below to P of A, and P of A defines a probability measure. Right, so one thing that I want to point out is that there's nothing that if I only write these things to you, this is all correct, even if I don't have tightness. Well, okay, it becomes a little bit more mysterious to see what's going on. But, okay, where was tightness used here? It was, okay, well, okay, so I can certainly find, why is tightness not used here? This is just a statement about finite measures, right? So this thing here followed from having a sequence of measures of total mass bounded by 1, and arguing that each of them had a subsequential limit. So we used the diagonal trick to extract a common subsequence for everybody. This increasing property that allowed us to define P, it's still valid, right? So there's nothing that requires you to have a probability measure here. So you still have a measure that's defined by an increasing limit. Like this. Okay? Right, so what do we get from this? Okay, let me say what I want to say here. See? Isso, a gente, yeah, so what I'm saying here is that if you define an increasing sequence of kj's, then you can say these things. I haven't said anything about that that I still have the PA is the weak limit of P and K. I have not said, right? So that's an important point. So if you have any increasing sequence of sets kj, if they're compact, then I can do all of this. Right, so let me save this for the timing. Now let's and we'll see why that's going to be important. Right, so that so that's only one argument. So we've shown that tightness implies by this construction that any sequence here is related has a convergent subsequence. Okay. Right. So let's define for each k. Okay. Let's define that. Yeah, maybe I don't even need this construction. But anyway, let's say I'm going to define alpha of k as the infimum of p of k for k contained in X, compactly. For p contained in X, belonging to S. Okay. So let's see. So S is tight if and only if for all epsilon there exists a k epsilon with alpha of k epsilon greater than 1 minus epsilon. And this is the same thing, let's say for all agree, of saying that there exists a sequence K1, K2, all compactly contained in X, such that alpha of Kn converges to 1. Right? Okay, so, or if and only if you want, that's the same thing as saying that the sup of alpha of K for K compact contained in F is 1. Okay. Right. Okay, so let's see. Let's assume, to get a contradiction, that S is not pi, but is relatively compact. Right. Right, so I mean, let me just notice in case someone missed that, right? So saying that the sup is 1 is saying that there exists a sequence of compact sets such as this holds. The only thing that I notice here is that you can take the sequence to be nested, right? So no big deal. So okay, now I'm going to take a nested sequence. Such that alpha of K of I converges to the sup of alpha K, which is less than 1. You can do that for the same reason. So you take any sequence such that alpha Ki converges to the sup, and then you make it nested, right? So you just take the unions of the sets. Okay. So right. And let's say there's less than 1 minus epsilon. Okay. So for each I, we may take Pi belonging to S such that Pi of Ki is greater than or equal to the alpha of Ki minus 2 to the minus I. And that's just saying, since this is supreme over measures in S, I can find at least one measure such that this is true. Okay? Right. And let's see. What else can I say? I can it's a nested sequence, okay, fine. And right. So now by relative compactness, I have that P, there's a convergence subsequence, right?
Where we have this inequality?
What?
The previous inequality.
The one? Well, alpha of Ki is an infimum, right? So, yeah, so it should be the other way, sorry. right? So it's saying, well, this is the infimum over measures in P in S. So I can find one measure that's close enough to this. But close, like it's a little bit above alpha Ki. Thanks. Right, so okay, so for all K, I have that okay, so now remember that what is it called? That for right, so I have measures, I have convergence, so I have limit. Where is it? Let's see. What? What? Oh, the portmanteau? No, yeah. So I have, for closed sets, I have that the lim sup is less than the limit of the measure. But, alright, so what do I want from this? I want that. Oh, there's something that I'm missing. Alpha K, infimum of pk. Okay. So I have, if I take, I'm saying that there's always a measure for every compact set. I'm saying that that's not right. Okay, and remember I wanted to use that proof to say what? No, this is not correct. Let's see. Okay, now I'm confused again because I want to give the topological proof, but I didn't define any topology, so that's not good. So now I want to just use the simple construction. How does the simple construction go? Okay, you have S that's not tight, so PI, KI. No, but PJ, KI, that's going to be larger than this. Yeah, I'm almost thinking I want to define the topology. Now I want to do the proof that I know how to do it because this is annoying. Because now, yeah, so the this should be the easy half. So it's the other half is much harder, in principle at least. Okay, right. Okay. So let me say sort of one way to solve this, which is not necessarily the best way, because I still need to prove something. So I'm just going to go around the proof and just say that, okay, so we know that we know the given tightness, we have okay, that we know that tight sets of measures are relatively compact. So watch. Now I just want to say that because you have this, yeah, but this is not what I want to do. This is less than what I want to do. Right. Okay, maybe I can. To do this without any topology. Let's see. I have this thing here. Okay, let me. Oh yeah, that's maybe that's what I want to do. Let's not say much. Right. So. Now that's. Yeah, I'm sorry. I know what's happening to me, but I'm really confused these days about these things. Because this should be the easy bit, the bit that you don't need to prepare before you teach, but that's not happening somehow. Yeah. So, what you know about the limit of compact closed sets in general, that PF is greater than the lim sup. PI menor estreito que que é menor ou igual a 1 menos epsilon mais 2 menos I. vejamos, espera aí. Não é tão simples, né? Porque... Mas o que você sabe? Você sabe, por exemplo, que PI de KI, PI mais 1 de KI, tudo que você sabe é que é menor ou igual... Ah, peraí, será que é isso? PI mais 1 de KI é menor ou igual que PI mais 1 de KI mais 1, que é menor do que 1 menos epsilon mais 2 elevado a menos 1. E isso só porque você tem de PI mais L, PI mais L de KI mais L, isso aqui você tem. Tá. Então você tem que o lim sup de PN KI é menor ou igual a 1 menos epsilon para todo I. KI. Se essa desigualdade fosse ao contrário, isso resolvia o nosso problema. Só que ela não é. Então... Right, so should switch back to English. Alright, so let's see. Right, so let me start with the easy bit, which is sort of that if you have a convergent sequence, then this set union P is relatively compact. Okay, so this is easier, and maybe this is going to help us a little bit. And right, so the proof of this is as follows. So for each, so we know that given epsilon, we know that there exists a k contained in X such that P of k is greater than 1 minus epsilon. So, okay, so how do we, okay, no, sorry, I need to do something slightly different. So, do you remember how we proved that a single measure is tight, that we found the compact set? So we did this construction taking open balls, right? So we need to take a countable dense subset. Say D equals to 1 m. So fix R greater than 0 and define A, M, R to be the union of the M first balls centered around these points. So we argued that A, M, R increases to X just because D is dense. So everybody is around the ball, is in a ball of radius R around one of these points. So for each, and so we know that there exists an M depending on R such that P of the ball up to MR R, this is greater than, say, yeah, maybe I should say that, yeah, this is greater than 1 minus epsilon r for any epsilon r that we choose. Okay, so we have this, right? Okay, so now what we're going to do here. So now we're in a good situation where we have open sets, and we can take, we can use the weak conversions to do things with open sets that go the right way. Right. Each set AMR is open. So lim N of Pn AMR is greater than P of AMR for all M and R, right? This means that if you take that Pn of AMR R is greater than P AMR or minus epsilon R, that is, it's greater than 1 minus 2 epsilon R for all R, for all n large. Okay. So the conclusion here is that for all epsilon R, and for all R, for all epsilon R, we can find MR such that Pn ui equals 1 MR of AMR is greater than 1 minus 2 epsilon R for all but finitely many indices. Values. Alright, so this is not. This is should be the bulk of n. Right. So I'm just saying the same thing. I'm just saying, well, I want to prove that this is true. I choose R. I choose epsilon R. So I know that P of AMR R is larger than this, without the 2. And because of this weak convergence property, I get this with the 2 for all large enough m. Now, okay, so now I wanna say that something slightly different. So for all R, for all epsilon, there exists an m depending on R, such that for P of AMR R is greater than 1 minus epsilon, and Pn AMR R greater than 1 minus epsilon for all n. So I almost proved this here, right? So here I say for all epsilon, I just take epsilon R equal to epsilon over 2, and I get this. So this is almost proven. The only reason why this is not proven is that there are a few exceptional values of n that I haven't covered. But that's easy to cover, right? Because we know that by increasing MR, then this we get this, right? So I'm just saying, okay, first take the MR that solves this for all but finitely many values of n, and then keep increasing this index until you cover the finitely many measures that are left, and you know you're going to do that. Okay, so in particular, for all, say k, there exists an m, an index I'm just going to call little m of k, such that p a m k are 1 over k is greater than 1 minus 2 to the minus k, and Pn a m k 1 over k is greater than 1 minus 2 to the minus k for all k. for all n. That's right. Now my compact set, okay, so sorry, there should be an epsilon here. So what do we want to do? We want to find a compact set that covers everything but an epsilon fraction of the space for all measures, right? So what is the compact set? We take the intersection in k going from 1 to infinity of the closure of these sets. The argument that we used last time is that a set is compact if it's closed, which this one certainly is, and totally bounded, meaning that it can be covered by a finite number of balls of a given radius. Right? So this set by construction is covered by a finite number of balls of radius 1 over k. And since 1 over k goes to 0, as k goes to infinity, for any radius it can find balls of that radius that cover the whole set. So this set, we proved that it was compact. And we have that Pn of k is greater than 1 minus the sum in k equals 1 to infinity of 2 to the minus k epsilon, which is just 1 minus epsilon for all n and also for the limit. Right, so this is the construction that we want to use. So maybe now I can prove this theorem. Maybe now I know how to prove this theorem. All right, so okay. Take S that's relatively compact. So let me try to say what's proven here, right? So the argument we have here is the following. So suppose that you have a family of measures for which for all r, for all epsilon, you can find an MR such that this holds. Then this family is tight. Right? So okay, so the claim is this. Okay, so the lemma is this. Suppose S is such that for all r greater than 0, for all epsilon between 0 and 1, there exists an index m such that for all p and s, p of A M R is greater than 1 minus epsilon. Then S is tight. And the proof is more or less implicit in what we did, right? So if we can always find these sets, then we can find a sequence of these sets with measure larger than 1 minus 2 to the minus k times epsilon, and with this radii decreasing. And we know that when you take these sorts of intersections of closures, blah, 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 you always get a compact set. Right, so this is the argument. And now this is going to be what we need, I think. Because, right, so now one thing to notice is that, this sequence AMR is increasing to x, right, when m goes to infinity. Right, again, so I'm claiming this lemma, and I'm saying that the proof is more or less what we have here. Well, okay, so how is the proof? If for all radii of the form 1 over k, you take the corresponding m of k. Then if you take the intersections of these closures, this must be a compact set by the argument from previous class. And it's a compact set, okay, so you take this with epsilon replaced to epsilon times 2 to the minus k. Then when you take the intersection of the closures, the measure is going to be larger than 1 plus minus epsilon for all p and s. Okay. Now this is fine because, right, so assume S is relatively compact. And for all m in n, there exists a Pm contained in S, such that Pm of A sub m r is less than 1 minus epsilon. Right? So I want to say that if S is relatively compact, there always exists an m such that for all measures you get the assumption of the lemma. Right? So assume that this holds, and we're going to get a contradiction. And now what do we do? So by relative compactness, we get the some subsequence of these measures converges to some p. Right, so let's say p of A m r is, by the properties of weak convergence, is less than or equal to the limit. Okay, maybe replace this by n. Okay. This is less than or equal to the limit infimum in J of P mj A n r, because A is an open set. Now look at this. As I said, these sets are increasing, right? So this set here is contained in A m j r for all j such that mj is larger than or equal to n. Right? Again, so this is a union of balls. This is an even bigger union of balls. You're taking more balls here. So this is less than lim infimum of P mj A mj r. And this, by what we wrote over here, is less than epsilon, 1 minus epsilon. But now we get a contradiction, right? Because this thing converges to 1 when n goes to infinity, because these sets are the exhaustive whole space. Okay, now it's good. Now it's really simple. I don't know why I didn't know this proof before. Because so we get a contradiction because it said, well, these measures are uniformly bounded by 1 minus epsilon. On the other hand, we know that these measures converge to 1 when n goes to infinity. Therefore, this thing here is these are contradictory assumptions. If S is relatively compact, there must exist an m such that this holds. Right? So without the case here. Therefore, you can always find a union of balls, a finite union of balls with measure greater than 1 minus epsilon, 1 minus epsilon to 2 minus k, and you're done. Okay, this is a lot better. Right, so I'm sorry this took so long. Right. Okay. Yeah, so I think that's the end of the proof per half. So one direction is really based on this lemma. And this idea that using these sets you can build a compact set, or the closures of these sets you can build a compact set. And then, so relative compactness means that it must be true, this assumption must be true for a family S. And the other direction is this complicated construction. Restrict to the compact sets, you get weak convergence over all of them, and then you take an increasing limit of the measures. So for next class, let me just say that we're going to talk about, so for the last few lectures of the course, we're interested in one particular complete metric space, or a Polish space, which is this one. The distance between two functions here. This. Right, so it's an exercise to show that this is a Polish space. If you want, so I mean, to show that it's a complete space, you just need to show that sequences of continuous functions that converge uniformly converge to a continuous function. And to show that it's separable, to find a dense subset, you just argue, well, polynomials are dense here by the Weierstrass theorem. But polynomials of rational coefficients are dense amongst polynomials. So polynomials of rational coefficients are clearly countable. And there are, so the compact subsets here correspond to bounded equicontinuous families of functions. This is the Ascoliar-Zella theorem. Usually we only prove one direction of it. And the one direction that we prove is saying that, well, if you have a family of functions here that's equicontinuous and bounded, then it had any sequence as a convergent subset. The other direction is sort of trivial. So the Ascoliar-Zella theorem actually characterizes compact subsets of this space. So this is essentially what we need to do probability in this guy. And our goal will be to construct Wiener measure. So that construct Brownian motion. And let me just say what Brownian motion is before we finish. So there's two things we're going to do here. So we're going to construct Brownian motion, that's sort of the easy part, and then we're going to prove the invariance principle. And just let me just say this thing. So, okay, let's say S of n. S of n is a sum of IID random variables with mean 0 and variance 1. So we know that if we normalize this sum by square root of n, you get convergence to the normal distribution. But let's say now you want to look at all the partial sums. So you take the interval 0, 1, and you divide it into parts of size 1 over n. Right? And you plot what you get. So here you have S1 divided by square root of n. Here you have S2 divided by square root of n. Of course, there are negative numbers out there, so you get this, you get this value here, sk divided by square root of n. And up to this point, so you get a bunch of points that are scattered around here. And we want to talk about continuous functions, right? So we're going to interpolate this. Oh, it's actually a lot less regular than this, but let me try to do my best here. Okay. So our continuous function is defined by Vn of t being equal to s, you take t times n from below, and you get, plus n times t minus n. Yeah, I think that's what it is. Yeah, s, t, n plus 1. X, Tn plus 1. Right, so this is what this linear interpolation looks like. So you take the sum up to Tn rounded below, and you take a remaining part, which is just the next term. That's it. When you move T. So each Bn is a random element in this space, so you can define a probability measure convergence. And the theorem we're going to prove is that these sequences here, they have a limit, which is Wiener measure. So like the central limit theorem, we have a limit that doesn't depend on the random variables that we put So the limit in the distribution doesn't depend on the distributions of these random variables. And well, we know a few things that this limit should satisfy, right? So first of all, we know that, so this limit is a measure of a random functions, right? So it's Bn is a random element of C, so this is a measure on C, on the Borel subsets of C. And so if B has distribution P, we're going to see that B of 1, well, this should have normal distribution, right? Because that's the distribution of the whole sum. If you take up to T, we're going to see that this is distribution normal 0 T. But you have an extra property, and these two properties actually define the process, which says the following. If you look at the process up to here, at this point, okay, so it's easier to put it this way. If you look at increments of the process over disjoint intervals, these increments are normal random variables and they're independent from each other. So say you take T1, T2, T3, T4, T5, and you look at the increments here, 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 here. These are normal random variables with distribution. A product of normal distributions with mean 0 and variance Ti minus Ti minus 1. And this is actually the way that Einstein, that Einstein defined the process. So he was interested in Poland moving in water, and he had an argument, and he had an idea that somehow that proved, or that was an argument, there was something that made the existence of atoms plausible, because if you put Poland in water, like a bit of Poland, it starts moving around the trajectory. That was discovered by a guy called, I think, Robert Brown, botanist. And this irregular trajectory, Einstein postulated it should follow this sort of distribution, should be a continuous trajectory of Gaussian increments in 2 dimensions in this case, right? And that the reason why Poland moved was that it was being bumped by atoms in the water. So the Poland was very light, but it was still not as light as the molecules in water. So the molecules would come and bump, it would move around, but it would take lots of bumps to be moved around. So somehow when you add up these bumps, you get Gaussian increments for the process. It's something like this, right, where we're adding lots of independent terms. But it took a while for mathematicians to actually make sense of this. The guy who made sense of this was Norbert Wiener, but that's why it's called Wiener measure. So essentially, all this thing about Prohorov and everything, the reason why, the only justification we give for this in this course is this business of Brownian motion. But now that we have all the tools, this is not going to be very hard to prove. Okay. Oh, by the way, this is all an exercise. It's essentially a matter of taking things you know and noticing that they imply that this is a Polish space and that you do have a characterization of compact subsets. Okay, thanks.